Okay, up to this point, we've done a couple of t-tests. One that compared CBT to the placebo condition, one that compared CBT to a combined CBT plus medication condition. But as you might have noticed, the treatment condition actually has 4 conditions or 4 levels to them. And the t-tests only do that, can only deal with 2 at a time. So really our question is why don't we do a bunch of t-tests? And the bottom line is at this point is when you do a bunch of tests, you increase the likelihood that you're going to make an error, a type 1 error in particular. We'll go into detail about this more in a later portion of the lecture. But what we want to do instead is use what's called an omnibus test, and what that does is that allows us to test all the means at a single time. So omnibus meaning that kind of covers everything. And ANOVA is one of those, is an omnibus test. It's one of those tests that allows us to do that. The problem, or maybe not the problem, but just sort of the consequence of that is that means there's some additional steps involved to get to the test that we're often interested in. As you get oriented to ANOVA, it's important to understand the terminology that goes along with ANOVA. ANOVA has it's kind of its own vocabulary. Okay, so the outcome is just called the outcome. So we're not really going to call that anything different. The predictor, in this case, so in regression we call it the predictor, the x's. Now we're typically going to call it a factor. And in ANOVA, the factors are all categorical variables. There is something called analysis of covariance that allows you to combine categorical continuous variables. But for our purposes, with one-way ANOVA, we're just dealing with categorical variables. Not always, but the categorical variable is typically unordered, something like treatment condition. And then usually you have 3 or more levels in your factor. You only technically need 2 levels. And if you only have 2 levels, then your ANOVA is just a t-test. And the one way, there's all kinds of different kinds of ANOVAs, and the one way just means there's just a single factor. As you add additional factors in an experiment or something like that, then you're going to have factorial ANOVA. And then there's repeated measures ANOVA and various ANOVAs for different kinds of designs. I think it's useful to start with the null and alternative hypotheses in one-way ANOVA. So the null hypothesis is that all 4 treatment conditions, the means in the population for those treatment conditions are equal to one another. So you'll see that they're just set equal. The alternative hypothesis says that at least one of the treatment means is not equal to another. Okay, so I've indicated this first set comparing CBT and medication as not being equal to one another, but it could have been any of these. It could be all of them. So when writing it out, it's arbitrary which one you choose. The idea here is that it's at least one. At least one mean is different from another. Okay, so just kind of staying along with the logic of ANOVA, the logic of those null and alternative hypotheses. You can think about the question that if the null is true, okay, we can say, are the treatments sampled from the same population? Okay, because if all the treatments were the same population, then the means don't differ. They all share the same mean, and so the null is true. So if that's the case, if the null is true and we sample from this same population, we're going to get several means, right? We're going to get several distributions. So you might have, say, one sample that looks like that, one sample that looks like that, another one that looks like that, and so on. We could do 4 of them. Let's do 4 of them just to make it, right? We could have 4 of them. And you can see that there's some differences between the means here, right? There's a difference there, and a difference there, and so on. We could do all the differences. So the question is, if the null is true, why do we see that? And the reason we see that is sampling error. Right? Those aren't true differences because we know that they're actually from the same population, so the only reason that differences would occur would be due to sampling error. So if the null is true, any differences we observe, we assume or attribute to sampling error. Okay? If the alternative is true, then are the treatments sampled from different populations in that case? Okay? So if you think about, okay, so if the alternative's true and there's some differences amongst the means, why would the treatment means differ? So let's think about that again. So we've got one mean here, or one distribution here, another sample, and, another sample, and let me do that one differently. Another sample, and then one last one, right? So now again we have these differences here, and here, and between these three, those sorts of things. So why would they differ? Well, we still have sampling error, because anytime we sample from a population, we're going to have sampling error. But we also have systematic differences because the alternative is true. So what we're going to do for ANOVA is we're going to use a set of procedures that are going to try to figure out, are the data more consistent with this or with this? And that's the idea behind ANOVA. So what we're going to do when we do the statistical test in ANOVA is we're going to create a ratio. What we're going to do is we're going to create a ratio that compares two variances. We're going to look at the variability between treatment conditions, and we're going to compare it to the variability within treatment conditions. Okay, if the alternative is true, okay, this is that second example on the last slide. If the alternative is true, then between treatment differences are going to be due to both systematic variance and error variance. And here, error variance, I'm just essentially referring to sampling error. Okay, so if the alternative is true, these conditions, remember, differ. I'll just do two of them here. The difference between these means here is due to both systematic sources of variability, because they're different populations, as well as sampling variability. Okay? And that, just to clarify, the difference between these means, right here, is that between treatment variability. The within treatment variability is the variability within each condition. Okay. So if the alternative is true, this between, right, is both things. The within is just the sampling error. If the null is true, then these differences are just simply due to error variability. Okay. Even these ones, right? This is still just due to error variability, and this is going to be due to error variability. So if we create this ratio and the numerator is about equal to the denominator, then we're going to assume the null is true. But however, if the numerator is bigger than the denominator, okay, then we're going to assume that the null is false. Okay, and we're going to reject it. So to create these ratios, we're going to go through and partition the variance just like we did in regression. So if you remember, in regression we partitioned the total sums of squares into the regression sums of squares and the error sums of squares. We're going to do the exact same thing here in ANOVA. It's just we're going to call them something different. Specifically, we're going to take the total and we're going to turn it in, or partition it into the sums of squares between and the sums of squares within. Okay, so if we ask, again, the total variability is the difference between all, it's the normal variance, right? It's the difference between all the observations. But this between treatment difference is to ask, okay, so we have this total variability. Let's say the total is this much. Okay, how much, let's say that much, is associated with treatment condition. And that much is associated with differences amongst people. So we're going to take the total and divide it into the between portion and the within portion. Okay, so this between portion represents how much of the total variability is between treatment means. The within portion is how much variability is differences amongst people within a treatment condition. Okay, and the sum squares between the sums of squares within add up to one another, right? It really is just a partitioning. Okay, our formulas are very similar to what we saw when we did this with regression. Okay, so to create the sum of squares total, what we're going to do is we're going to take the outcome variable. So this is yij. This means the observation on the outcome for person I in condition j. Okay, person I in condition j. So you take, to get the total, you're just looking at how do all the individual observations vary around the overall mean, right? So the average. Okay, so if we put this in terms of the variable in our study, right? Minutes awake after sleep onset. This is each individual's observation on the wake variable, and this is the overall average. These are sums of squares, so we take the difference, square them, and then add them up. Okay, so the sums of squares between takes these things. Okay, these are group means. Okay, because this is the mean for condition J. So in the case of our example, we're going to have 4 group means. Okay, because we have CBT, we have medication, we have their combination, and we have placebo. For this one over here, this is again the 4 group means for the wake, and then this is the overall mean. So these values are the same across here. So you can think of the sums of squares between as the variability amongst group means. Okay. Now let's look at the sums of squares within. Okay, so again we have each individual's observations, yi sub j, okay, minus, now we're subtracting the group means, so we're looking at the variability of each individual observation around its respective group means. So you can think of this as, like if we take each individual's wake score and we subtract it, so let's say I'm in the CBT condition, this is going to be my number of minutes wake up around the average or the group value for everybody in the CBT condition. So it's how do I differ from the average person in the CBT condition. Okay, so what that's telling us is the within represents the variability within a group, or variability around group means. Okay, so that's going to, if you remember, this guy, sum of squares within, gives us our estimate of sampling variability. And that makes sense, because if I'm randomly assigned to CBT, the only reason that I would differ, the logic goes this way, the only reason I would differ from anybody else who gets CBT is because of individual differences, right? Something unique about me as compared to another subject in that condition. We all share the same treatment, so that can account, systematic differences between treatments can't account for any differences between people who both got CBT. Okay? Whereas this one, the variability amongst the group means, is systematic variance plus sampling variability. So individual differences affect this variability here, the sampling variability, right? But also systematic differences, because now we're comparing group means, right? People who got CBT versus people who got medication. So let me go back to this slide here, where we're looking, we're going to make this ratio. This is we're going to create an F value for this, okay? And so if we scoot back ahead in the slides and we look at how do we create that ratio, okay? So what we're going to do is, here's our F down here. This is what we're building to. And so we say the F is equal to the mean squares between over the mean squares within. Okay, so this is that ratio of the between group variance to the within group variance. Okay, so the way we get to the between group variance is we take the sums of squares between, thing we just talked about on the last slide, and we divide it by the degrees of freedom between. Okay, where the degrees of freedom between are equal to k minus 1, where k is the number of levels of our factor. That's what K equals. Okay? And so it's 4 in this case. So our degrees of freedom are 3. All right? So if we take our sums of squares between, we divide by our degrees of freedom between, then we get what's called the mean square between. It's essentially the average. When it says mean square, it's saying, the average of these sums of squares. Okay? Or the average of the differences would be a better way to say that. Okay? So then we take the sums of squares within and we divide it by its degrees of freedom, where n is our total number of subjects and k is the number of levels of our factor. Okay? Okay, and then we take our mean square within, and that's, we take the ratio of those two things right here, and we get our mean square within. So that's the average of these differences. And then the f, okay, is the ratio of this thing to this thing. Okay? And mean squares are variances. If you remember the formula for variance, it's x minus x bar squared over n minus 1. That, right? So it's the sum of x minus x bar squared over n minus 1. So it's just, it's these sums of squares over a function of n, right? And that's all we're doing here. We're computing variances. Right? Those are just specific variances. This is the variance between, and that's the variance within. Okay, so once we have all that stuff, we're going to go ahead and create what's called an ANOVA source table. And this is an example of an ANOVA source table. And source tables in analysis of variance are roughly the same. You're going to see most statistical programs output a source table that looks kind of like what you see here on the screen. Okay, it's called the source table because it divides the variance into its sources. Okay, you got the between variance, the within variance, and then a total. Then you have a column for the sums of squares. You have a column for the degrees of freedom. Okay, so then the mean squares, and the mean square column is this divided by this. This one is this divided by this, and then your f is just this divided by this, right? So it presents it nice and compactly, and we'll see when we look at this in Stata that that this is exactly how Stata presents it, which is kind of nice too. And seeing it in Stata, we'll be able to get numbers, and we'll walk through interpretations and stuff. But it's pretty important for you to know the structure of a source table. So if you're going to memorize some stuff, this is one of the things I would memorize. I would memorize sort of what is the structure. So what are these columns? What are the degrees of freedom in a one-way ANOVA? Okay, for each source of variability. How do you construct the mean squares? Okay, so if I were to give you a sums of squares and some degrees of freedom, construct the mean squares and f. Or if I were to give you a description of a study, give you the sums of squares, if I tell you how many subjects and how many conditions there are, you should be able to take the sums of squares, figure out what the degrees of freedom are, and work toward your f just by knowing the design. Okay, so those are the kinds of things I would like you to know, because I think it's a useful thing to memorize and get down with some of these simpler designs. Once you get to more complicated designs, memorizing them is probably not worth your time. All right, so I have the insomnia data loaded here. And so now we want to see how to do the one-way ANOVA. There's a couple of ways to do it. So the first is we could say one-way, wake min, and then condition. Okay, so this is like the regress command where the dependent variable, the outcome, comes first, and then your independent or your factor variable comes second. Okay, the one-way command will do a one-way ANOVA, which is great. So if we want to see that, we can look at it over here, and you get your source table. So you can see you've got the the source of the variability over here, your sum squares, degrees of freedom, mean squares, f, and then your p-value for the f test. Okay, so as you walk through this, I think it's helpful, and we can review this in class. Make sure you know where these mean squares come from and how the f test comes about, right? So as you review it, remember you take your sums of squares, formulas on the earlier in the lecture. You divide by your degrees of freedom. We had 4 groups, and so we have 3 degrees of freedom here. If you take the sum squares, divide by degrees of freedom, you get a mean square of 6281. Same thing for here. Take the sum squares for the within groups. We had 120 people. 4 groups, n minus k is 116. Okay, so you get a mean square of 215. This f comes from the ratio of those two things. And we'll talk about how to interpret this f and all that sort of stuff in a later video. But at this point, what we would say is we would reject the null hypothesis, okay, because this p-value is less than alpha if we set alpha to 0.05, and we would assume that these means are not all from the same population. A second way to do this is to use just the straight up ANOVA command. And it follows the same pattern of outcome then factor, which is what pretty much every stata command uses. Okay, it gives you this more generalized source table. Generally, I just use the ANOVA command, just because you're going to use it for other ANOVA designs that we're going to cover in this class, and then other ones that you would do. And so I like kind of having the unified perspective. One thing you'll notice from the ANOVA command is it gives you this extra line in the source table called the model. This is exactly like the regression sums of squares in regression. So in regression sums of squares, you get the variability associated with all the predictors in the model. And that's what this model sums of squares does here. Now we only have one predictor, so it's the same thing as condition here. But as you do factorial ANOVA and other sorts of things, you're going to see that this model sum of squares is going to be different. I never use this in any of the analysis of variance sorts of things that I've ever done or seen or read about. So I don't totally know why Stata puts it in there, but it's in there. You can largely just ignore it for our purposes in this class. Okay, so these are your, this is your between sums of squares, your within sums of squares. You'll see, you can look up here, it's the same numbers as before. So your preference when you're doing one-way ANOVA, whether you want to use one-way, the one-way command or the ANOVA command, they're just fine. I'd probably encourage you though just to start using this command generally. And that is how you use the ANOVA command.